Hello everyone, my name is Faisal Ghaffar. I am PhD student at Academia Sinica, Taiwan in National Tsinghua University, Taiwan. I am working under Professor Dr. Meng Chang Chen and Dr. Chia Shin. The topic which I am going to present is last Location Estimator Scheme for PM2.5 sources in Sparse Sensor Network. First, we will go through introduction, then our model, finally the results, and then conclusion. Air pollution occurs when harmful or excessive quantities of substances are introduced into Earth's atmosphere. So the causes of air pollution is the economic growth, the rapid urbanization, energy consumption, and agricultural activities. Its effects can be seen on human health. The economical and social effects are also seen. It also has environmental effects, and the effects on wildlife has also been observed. The major pollutants are mentioned here. Our focus is more on PM, which is particulate matters. PM2.5 or the suspended solid and liquid particle in air, and it is mainly divided into two categories. One is called PM10 and other is PM2.5, based on its size. The sources of PM2.5 are construction sites, unpaved road, fields, fires, or maybe some others too. The harmful effects can be seen that it goes deep into the lungs. It can also goes deep into the bloodstream and causes many chronic diseases. It also reduces the visibility. So therefore, it is necessary to detect, forecast, and locate the pollution sources so that people should be aware of their situation around. And also government needs these detection, forecasting, and locating so that they can make strategies and take necessary steps to control the pollution sources. The government monitor these pollutants through EPS stations. These EPS stations are quite very large space. It's shown here in the figure. It's quite expensive, and it cannot be deployed at higher density because of the space and the cost. So it is very sparse. That's why it cannot be used for locating pollution sources, especially local pollution sources. The IoT-based pollution sensors have currently are in use. As the part of smart city projects, many cities have densely deployed low-cost sensors, such as in Taipei and Zurich. It can be deployed in room, it can be deployed in office, and it's also low cost. The problem is that it requires community involvement, and people need to buy these devices and install it in their houses. That is why in practice, deployment of these sensors are lower than expected. So to estimate a local location of pollution source, we need to make a model based on these sensors so that we can accurately estimate the location of pollution sources. Coming to a problem statement, let's suppose we have a pollution source P, and an pollution event occurs from this location. So the wind actually spreads this pollution from this location to the location of these sensors and all the surrounding areas. So when S2 detects the pollution source, here we see the reading of S2 has gone higher. So we say that something has occurred at the pollution of S2. That can be a pollution event. And we mark the S2 location as a pollution event location, although the pollution has occurred a bit farther. So the objective of this work is to model the PM2.5 spread from this pollution source to the surrounding sensor. And second is to minimize this distance D2, the estimation distance, and the actual pollution source location distance, so that we can say that the pollution event has occurred at this location instead of this location. So to make a background for our further model, we say that this center point represents the pollution source. If all the surrounding sensors receives equal amount of PM2.5 concentration, then a center, of course, represents the pollution source, but that is not the case actually. Some of the sensors are nearby and some sensors are far away. So those sensors cannot receive equal amount of PM2.5 concentration. It is based on wind. It is based on how much of the PM2.5 concentration settles down when it flows through the air. Instead, every sensor carries its own weight. It receives its own influence from this pollution source. And if we can calculate the influence of each of the sensors, then we will be able to calculate the location of this pollution source. So the pollution spreading has two domains, one spatial domain and one temporal domain. First, we will explain the spatial domain. In spatial domain, the dispersion occurs through spatially from this pollution source the pollution spreads to S1, S2, and S3. And it is dependent upon the wind, it is dependent upon how far or nearby the sensor is, and the third one is how much angle is between this wind vector and the sensor vector. So three things we have. One is wind, the second is this displacement vector, and the third one is this theta. When we combine all these three with dot product, we can easily calculate the strength of this pollution which each sensor can receive, like this here. When theta is 0, we can receive maximum strength. When theta is 180, we can receive minimum strength. Coming to the detail of these three things which we already discussed, the first one is the magnitude of wind vector. The magnitude of wind vector is we can actually calculate it from the speed of the wind. So Vjt is the speed of the wind at the location of the pollution source at a particular time, and is computed like this, whether beta and gamma are constant. When wind speed is actually 0, the wind can still diffuse to the surrounding environment, and that's why we have included a beta. The gamma is a time constant, and it shows the amount of time for the pollutants to settle down. Coming next to the magnitude of a displacement vector. This is actually the Euclidean distance from this pollution source to the sensor. So this is actually a displacement. The third one is the theta. This theta is calculated from the difference of the bearing angle of the wind, which can be provided by the sensor. Normally, a wind sensor provides its speed and also its direction. So you can easily calculate this bearing angle. We don't need to actually calculate, the sensor provides it. The second is the bearing angle of this sensor, this sensors and pollution vector. So we call it the displacement vector D. So when we want to calculate it, we know the location of pollution source. We also know the location of sensors, so we can easily calculate this bearing angle through this equation. When we calculate both of these theta, then we can subtract one from the other one and calculate the angle between this one and this one. So there is also a decay occurs. The decay means that how much of the pollution settles down when it flows further. So the concentration becomes lower as a function of distance. When it flows from this pollution source to this location will have higher concentration and this location will have lower concentration. So that is why we need to normalize the earlier calculated the strength which each sensor receives. So this decay can be either linear, quadratic, or cubic. But to avoid constants, we have introduced dynamic decaying function, which is dependent on distance to step ratio. So the distance to step ratio is actually how much the decay occurs at how many steps actually. Like here we can see that after 200 meters, we say that the decay occurs. So this alpha is actually further, the step constant is further dependent on the angle. The angle with the wind is smaller, we say there is smaller decay. If the angle is much larger, we say that there is quite frequent decay and occurs every 100 meters. This figure shows the spatial dispersion of PM2.5 from this pollution source. The pollution is spread to these sensors. This side is in the direction of wind, and this is opposite direction of wind. In the wind direction, we have positive influence, and this direction we have negative influence. Here in this 3D figure, we see that the nearby sensors, this one and this one, receives higher concentration, and it's also in the direction of wind. This is higher positive, and this is higher negative. If we move away to this place and this place, the concentration, the influence which each sensor receives is smaller. And the sideways, when the angle increases, like this one and this one, the angle is increased. So these two will have lower influence of the pollution spread. Coming to a temporal variation, when a pollution event ET occurs, at time t, there will be a temporal increase in PM2.5 concentration, and it provides the evidence that the pollution content has reached our sensors and source lies somewhere around the sensor. Some of the sensors, there will be increase, but for some sensors, there will be no increase. There will be decrease or exactly no increase or decrease. So we calculate the temporal strength by quantifying the temporal variation in its concentration through this equation. And this equation, the MIT is the actual concentration of PM2.5 at sensor SI, while NIT is the normal concentration and normal range when there is no pollution source, when there is no pollution event. And the NIT is actually calculated by the NMITs, for example, last 1 week or last 1 month. The resultant strength of each sensor is then calculated by combining the spatial strength and temporal variation strength. When we combine these two vectors, we get a final strength, which we call the strength of each sensor. Here we see that when the pollution is spread to these sensors, this one receives a negative temporal strength, while earlier we saw in the figure that all of these were positive. This negative comes because there is no increase in the temporal strength. When there is no increase in the temporal strength, it means there is an obstruction which is not allowing this pollution to reach to the sensors. So these sensors become positive, these sensors becomes negative. Only these sensors remain positive. These sensors will receive positive dispersion actually. So coming to allocating pollution sources. Using the spatial temporal score which we already calculated, the source location can be then estimated based on the principle of center of gravity. To do so, we take n sensors around a sensor and consider a sensor as a particle of an object, each of which has a mass. The resultant spatial temporal strength of each sensor is considered as mass of the sensor and treat source as the center of gravity. So in first step, we convert the latitude and longitude of each sensor to a Cartesian coordinate system. Then in Cartesian coordinate system, we calculate the location source based on the weight of each sensor by combining it with each coordinate. Finally, we convert back to geographical coordinates. Coming to average performance of our model, it shows that LOST has average closeness performance of 1099 meters compared to the other, which has very higher. Also, we see that 80% of the location which we have estimated lies below the range of 2000, while the others have the same and 2500 meters are much more higher. We also calculated the failure ratio of our model in comparison to the other models, which is k in nearest and center point. The nearest one is the nearest sensor actually. So we see that the LOST has lower failure ratio of 6.5% only, while the other sensors has very high. We also see that 80% of the failure ratio is in the nearest distance. In higher distances, the failure ratio is very smaller. So we can say that our sensor performs much better when the sensors are very sparse. Looking at these trends, when we increase the number of sensors from 5 to 25 here, when we increase the sensors from 5 to 25, we see that there is no increase or decrease in average closeness in our method. But in other methods, if we increase the number of sensors, the performance degrades. Here we see the center point, the performance is increased from around 1700 to around 3500 or something. We also see that when we increase the number of neighbors, the failure ratio decreases. The second trend which we will observe here is between the normalization constant or the decaying constant. In the decaying constant, we have used linear, square, cubic, and our dynamic method. We can see that in dynamic method, the closeness is much more smaller in comparison to the others. If we look at the failure ratio is almost the same, just only a 1% or 2% difference, but the closeness is much more smaller here in dynamic. So we say that dynamic is performed much better than the linear, square, and cubic decaying methods. Coming to our future work, we aim to include the following additional work with our proposed model: detecting pollution sources, predicting the spreading time, and also the spreading concentration from a pollution source to specific location. Coming to conclusion, finally, we propose LOST, a location estimator scheme which locate pollution sources of PM2.5 in a sparsely deployed sensor environment and a relatively closer distance. We developed a model for the dispersion of PM2.5, then used the sensor strength to calculate the pollution source location using center of gravity. And also we did a comparative analysis with other methods, and we have seen that LOST is capable of estimating the pollution source with higher closeness.